All right, so today we're going to be covering cells, modules, and arrays. A cell is the smallest individual unit that a PV system could have. One solar cell is going to output about 0.5 volts. A lot of people get confused at that because they think that the size of the cell has something to do with the voltage. And that is completely inaccurate. The voltage output by the cell is primarily driven by one factor, and that is the temperature of the cell. The higher the temperature, the lower the voltage output. Sure, under the same conditions, the larger the surface area of the cell, then the larger irradiance that it is going to collect. Therefore, the more current it would output. Yes, yeah. And so the individual cell, its size is very, very relative. I have seen solar cells that are approximately 1 foot in diameter, round. It's about the largest ones that I've ever seen. There are some that are so small you could barely make them out with the naked eye. And the reason being is that they can be cut or broken into smaller pieces, and output the same voltage. And so it gets people confused because if I were to have a solar cell, and I've got some in this box, I'll pull one out. Let's say this is about 1.5 by 3 inches in size. And I were to take this cell and I were to check the voltage that came out of this cell with a voltmeter, it'd say 0.5 volts or 0.6 volts. If I were to break it in half and I were to check each individual half and the voltage that came out of it, each individual half would have the voltage of 0.5 to 0.6 volts. Breaking it into smaller pieces does not change the voltage. One of the ways that you might compare it to would be a balloon. A larger balloon does not have to have a different pressure than a smaller balloon. Theoretically, you could have the same pressure in a smaller balloon as a bigger balloon, but the bigger balloon would hold more water. All right. And so if that's what we're talking about in the electrical sense, voltage is pressure. Amperage is the volume or the flow of the water. And so for this cell, think of it like a balloon. A bigger balloon does not have to have more pressure, but it will output more water. Therefore, it will output more current. So the size of the cell is the bigger factor to determine the current that individual cell would output. So let's say that my device that's going to be powered by this cell is extremely low amperage, 0.001 amps. Theoretically, I could take a laser and I could cut this one solar cell into 10 separate cells, connect them in series, and make the voltage output go up by 10 times. Instead of having 0.5 volts of output, this same amount of material could have 5 volts of output. But if this had 5 amps of output under ideal conditions and I cut it into 10 sections, then each of those sections would be reduced down to 0.5 amps. And so depending on how you have cut your cells and wired your cells, you can dramatically change the amperage output of the individual cell by reducing its size, or increase the total voltage by cutting it into smaller cells and wiring them into series. Well, what is a solar cell made of? Well, the main component is some type of a semiconductor. And a semiconductor is a material that has properties of both an insulator and a conductor. Hence the term semiconductor. At lower temperatures, they tend to behave more like an insulator. At higher temperatures, they tend to behave more like a conductor. Now that confuses people whenever you realize that the colder that these cells are, the higher their voltage output. It almost seems like counterintuitive. Well, the voltage output goes up, because whenever you have a lower temperature, even though it might behave more like an insulator, whenever it's exposed to bright sunlight conditions, that insulation factor is overcome. And now that it is colder, you have the individual molecules or atoms closer together. And so you have a shorter distance for the electrons to jump from one to the next, to the next, to the next. So you have a lower conductive resistance. All right. At the higher temperatures, you also get more degradation. If you're going to operate this device at an extremely high temperature for years and years and years, it will break down and it will wear down quicker. Doping. We take a pure semiconductor. And when I say pure, I do mean pure. 99.9999% pure silicon. Even one part out of a million parts will dramatically affect the semiconductor qualities. The main purpose is to create N-type and P-type silicon. N-type being doped with phosphorus, P-type being doped with boron. Phosphorus has an additional element. So P-type being a positive charge carrier, N-type being a negative charge carrier. Boron is used to create the P-type. Phosphorus is used to create the N-type. What's the difference? Well, boron has one extra boron is the P-type, which means that it has one short electron. So it has an electron hole. All right. It would like one extra electron to become balanced. An electron having a negative charge would gravitate towards a boron atom that has one short negative charge. It has a one positive charge. Whereas with the phosphorus, it creates the N-type because phosphorus has an extra atom in its outside valence shell, an extra electron in its outside valence shell. And so it being and having an extra electron, it's referred to as a free electron. That electron can leave the boron atom relatively easily if it is attracted to another atom, for example.
Phosphorus.
You what?
You said leave the boron.
Oh, I'm sorry. Yeah, leave the phosphorus, and the phosphorus would have the extra atom. So, this isn't a chemistry class, but it will make a lot more sense why we've picked the elements that we have. In this middle chart right here, we see rather balanced elements. We have silicon, we have gallium right here, lead. These things don't have a high reaction rate necessarily, all right? But just to the left, we have boron. Just to the right, we have phosphorus. And so just to the right, we have one short electron, and just to the left, we have one extra electron. So you will typically find the doping agents to be located relatively close to each other as far as column-wise. Why? Because all of these elements have either one extra or one short electron in their valence shell. It's part of the reason we continue to try new chemical agents, both for the semiconductor and the doping agents involved with the semiconductors. One of the other things is to arrange the semiconductor atoms in a more organized fashion. The more of them that we can get organized, the closer that they are together. So that's where a crystal comes in. A crystalline material means that all of the atoms are organized in a structure that they are rigidly attached to each other. Picture a crystal in your head. Does it bend? No, it just shatters and breaks, all right? Because it is so locked together that there is no room for wiggle amongst those elements at the elemental level, basically. So we already know what the photovoltaic effect is, and that is where solar radiation is turned into electrical energy by a PV cell. More specifically, it is photons that are causing electrical movement and creating a voltage potential. That voltage potential is arriving between an N-type and a P-type. So I have one type of silicon that's got extra electrons. I have another type of silicon that's got a shortage of electrons, and I put the two of them together. The boundary between those two is referred to as the P-N junction. Now, some people think that P-N junction is a special material. No, it's not. It is just where the two of them come together. And what's special about it is the electromagnetic fields that are created by having that P-N junction. Well, I mean, it's where the two layers, one that's positively doped and one that's negatively doped, join each other. Where they touch each other, they're just touching each other. That's exactly right. No, no, no. So you have a p-doped region and an n-doped region. In the p-doped region, you end up having electron holes. In the n-doped region, you have electrons, additional electrons. Well, they automatically end up wanting to cross. All of the electrons, once you put these two things together, cross over and go into the p-doped region, and all of the electron holes come over to the n-doped region. And so you end up with having a whole lot of negative charge and positive charge right next to each other. Basically, almost like a magnet. You have a strong pull on one side and a weak and a strong opposite pull on the other side. So the n-doped region is the top of the panel. It's the panel where the sun is striking, typically. All right, and so the electrons do not easily move through this region. Why? Picture it. You're an electron. You're floating around over here. You are repelled by these guys. You try to come here, but just like a magnet, I can't go there. I'm pushed in the opposite direction. Okay? So you manage to find your way through a series of wires and get back here. Well, suddenly, if you're on this side, you are automatically attracted to these guys, aren't you? So you are pulled through here, but as soon as you get here, you are spit back out into this open region, and you can only move in one direction. That's called a diode. A diode is an electrical device that will only allow electrons to flow in one direction. That p-n junction has created a diode to where the electrons want out of the top. In fact, there's pressure for them to get out of the top, but there's no path for them to get through this middle region. If we provide them a path around to the back, they will go through the load, assuming they can overcome that resistance, and they'll rejoin. All right. The power to motivate them to do that comes from the solar radiation. All right. The electrical field that is created here is just like a magnetic field, and it is very difficult to push one northern toward another northern. It's very easy to push or pull a positive and a negative together. Why do we use silicon? We'll start with it's unbelievably abundant. It's the second most abundant element in the Earth's crust. Like 15% of the Earth's entire mass is silicon. We're not going to run out of it. It's very, very easy to find. Therefore, it's relatively cost efficient to harvest. Our cost for processing silicon is not the harvesting of the raw silicon. It is the processing of that silicon into a purer format or a purer material. That is energy, basically, that we're using. The cost performance ratio is one of the aspects, but we also have to figure a safety aspect. Silicon is relatively safe. It's not chemically toxic to us or to the earth. If you were to leave a bunch of raw silicon in a farmer's field, you're not going to get polluted crops or a dust that is poisoning or anything along those lines. The other thing is it's very recyclable. Again, we have to use energy. We've got to melt down and separate it and purify it. Currently, we are just starting to approach the cost curve parameter that the recycling of solar panels will be cheaper to get the materials needed to make solar panels than the harvesting of raw materials. Currently, it is actually cheaper to harvest raw aluminum, process it, turn it into a solar panel. Raw silicon, harvest it, and turn it into a solar panel. That is actually cheaper to do than taking used solar panels, reprocessing them, and turning them into fresh solar panels. But we're not far away from that. In fact, in Europe, there is a system called PV Cycle, and the cost of recycling every solar panel is built into the sales cost of that solar panel. Okay? It is not the most efficient, though. I will tell you that silicon is not the most efficient of the semiconductors, and that's why we don't exclusively use it. So, what are the other semiconductors? Well, the most efficient solar cells are made of gallium arsenide, and the doping agents are arsenic. Why would we not use this commonly? Poisons. Arsenic is very, very toxic, and it's not just like for humans. It gets into the water, it gets into the foods. In fact, there are places in Asia or Europe, the Middle East, India, Myanmar, I believe, that there is naturally occurring arsenic in the groundwater, and if they irrigate rice fields or crops from the water, the arsenic is absorbing into the rice, and then the rice is giving arsenic poisoning to millions of people in those countries. It is a major environmental issue. Why was it never before? Well, because in the past, those countries always used surface water to irrigate their crops. Well, now that they're getting different varieties of crops, more modern technology, they're tapping into underground water sources. They've already built the infrastructure. They operated it for years and years and years. And suddenly, like, our arsenic levels of our populations are dangerously high. Why? Because our water source changed. That was just for irrigating crops. How many people may be drinking that water and actually getting it directly, not even through the crops? One of my past environmental sustainability students did a presentation on it, and even I was shocked at the arsenic levels. Main application for the gallium arsenide cells are space applications and space limited applications. Okay, so extraterrestrial would have been a better term for me here for space applications, extraterrestrial applications. So the International Space Station actually has gallium arsenide cells on it. If you were to have a damaged solar panel in space, it's highly unlikely that it would ever pollute the Earth's environment. It's also thought that solar panels that are in space probably will not be recycled for a very, very long time, if ever. And so we're not quite as concerned about what do we do with these panels while they're biodegrading and breaking down. It's not like we can go put them in a landfill or something like that if they're gallium arsenide. There are some applications on Earth like concentrating solar. So you have a giant magnifying glass and it concentrates to one small cell. Well, obviously you want to use the most efficient cell that you could have made for a concentrating solar system. And so gallium arsenide cells are used for concentrating solar. Or if you had an application that you needed the most amount of power produced in the least amount of space and money and safety was not a concern as much. Let's talk about an airplane. Airplanes that are solar powered. They have them that can stay up indefinitely. All right. They charge themselves enough during the daytime that they can glide and fly throughout the nighttime. They have to stay above clouds so that they don't get the cloud coverage. Also realize that the higher they go, the lower their air is. Their air mass reduces. And so there's neat applications, but you got to have the most efficient cells possible. And so for an application like that, gallium arsenide cells. Because we have gallium arsenide cells here on campus. We have a variety of them. Most of them were donated to us by Lockheed Martin for the building of one of our solar racers in there. We do have to be a little more cautious that we do not dispose any of our gallium arsenide cells in landfills. Obviously, their applications are a high cost and harmful for the environment. Their manufacturing processes also are a lot more expensive because they have to deal with all the hazardous chemicals safely in that manufacturing process. Excuse me. So we have several other types of cells. To start with, we have thin film modules, and those are deposits of one or more thin film of PV over a substrate. The reason that we say one or more is because different thin film materials are made of different elements that can absorb different wavelengths of light. So if I have one cell layer that will absorb wavelength A and another one that will absorb wavelength B and another one that will absorb wavelength C, then I can increase my total efficiency from that cell. I can even add to that remember how I talked about we have an N type and then we have a P type? Well, what would happen if I would put another N type on the bottom of that P type? Now I could actually produce power whether the radiation hit the bottom or the top of the cell. Now we have a bifacial panel. That is exactly right. All we've done to the whole cost of manufacturing is add one more tiny layer to one component. So the cost of manufacturing a bifacial solar panel is pennies more than the cost of manufacturing a standard monocrystalline solar panel. In fact, theoretically, if you were using something like Amorphous, you could thin film print on the front and the back of the panel and still have the exact same production capabilities no matter which direction that panel was turned. There's some of these thoughts of actually creating like a bubble. All right. Imagine like a solar bubble. No matter where the sun was shining, it would have the same amount of surface area, like its own tracking system. All right. It wouldn't matter which direction it would turn or rotate. A semicircle would probably accomplish the same thing, but theoretically, if it was a bubble, it would be floppable. So any of the energy that struck the ground and came from the bottom, it would also be able to produce power.
We're talking about a single cell bubble?
Right. Okay. Or we're talking about the surface of the cell to be made of bubbles. Imagine if, if in a low weight or a no weight environment, the liquid silicon were to be the powdered silicon mixed with a liquid were to be printed in tiny little bubbles to where if they dried, they still retained that same shape, basically. You guys know that you can blow a bubble and put it in a freezer. And as long as it doesn't pop, when it freezes, you end up with a physical frozen structure like a bubble. All right. The same theoretically could be done for the manufacturing to increase the surface area of the cell. The larger that surface area is, the more opportunity that it has to absorb the solar radiation, and the less likely that you get it to bounce off.
So, if you did create a bubble cell, you still won't get 0.5 volts,
That's right.
no matter what.
That's exactly right.
But your amperage will go way up, so
Sure.
that keeps it from burning up. Because you barely have any voltage to allow that current to go through.
Well, I mean, the term burning up,
You're pushing a lot of amperage.
right, but the resistance is not being turned into heat. So you should not ever have a problem with having higher amperage produced by each individual cell. You might have to have bigger conductors theoretically, but
so whatever it goes into.
right after it's made all of its series connections and it's going into like the leads that come out of the wire. Right now, about 15 amps is about the highest amperage that any of them output. And I would say that if you got much more above 22 amps, then you'd have to have larger than 10 gauge wires, just for safety factor. So thin film modules can be printed out of a variety of materials: amorphous silicon, copper, indium, gallium, selenide, cadmium telluride. There's even some materials now called perovskites, which is basically a chemical that is printed, but it naturally forms this structural shape that increases the surface area. The problem is that shape breaks down. And so over time, well, not over time. Right now, the government is spending billions of dollars around the world to increase the perovskite technology. And it is thought to be the next level if we can get it to be stable. Right now, solar silicon cells will be stable for 30 years. That's why they have a 30-year warranty. But these perovskite cells are only about a 10-year stability. And so the labor to replace the panels every 10 years is not justifying the reduced cost to produce these perovskite type panels. All right. Someday, if we have time, we'll do some more. That's a future thing, all right, for sure. Advantage of these, to start with, they're almost always lower cost. And when we say lower cost, normally we mean the cost per watt to produce. All right. If you want a 100 watt amorphous panel versus a 100 watt monocrystalline panel, it's going to be cheaper to make the 100 watt amorphous crystalline panel. All right. It uses less materials. It is less efficient though. So if you have a space issue, like, hey, I've only got 4,000 square feet of roof space and I need this much, you might not be able to meet your need with the lower efficiency panels because they'll take up more space. They also may not be as durable. Now, this is a thing, may not be. When we're talking about durability, we're talking about how long will they last and perform under normal conditions. These things can be printed on flexible substrates. So give yourself an idea of, you got a sailboat. When there's no wind, how do sailboats propel themselves? Modern times, not ancient times.
With motors.
And how do they power the motors?
Usually either with fossil fuels or there's some with electric motors.
Even then, the fossil fuels are almost always going to run a generator. Yeah, and it's going to be an electric motor that's turning that turbine or that propeller. And so I think that we are, I know it sounds weird, we're going to go back to where our transportation across the ocean is powered by the wind and the sun. All right. We already have a container ship that is automated. It leaves China with no people on it, and it is powered by the wind and the sun, and it drives itself until it docks. The greatest fear with that is pirates. Somebody could jack that ship pretty easily. All right. But the reality is humans are expensive. And if you're not quite as worried about like rush, we're not talking about medical goods or food or something like that. It doesn't matter if it takes 3 weeks or 5 weeks. We just want it to be cheap. Whenever it's sunny, it moves by solar power. Whenever it's windy, it actually has turbines that are vertical axis turbines. So no matter which direction the wind is blowing, it makes those turbines go around, and it uses that for its propulsion mechanism. All right, virtually no emissions. And in those situations, you want to be using a type of a cell that is very durable. If you have a flexible on a solar sail, that sail could actually catch the wind physically and catch the sun electrically.
Not to mention covering the actual bow.
Sure, but that is a very
You have
durable. You have to have very durable material, because the wind is whipping it all the time. The salt on the ocean is very corrosive. And so, surprisingly enough, some of these canvas solar cells, they are very durable. It's the military that has made them durable, though. The military is one of the largest organizations which is converting to solar, and they have flexible solar that will literally hook up to a Jeep and unroll out of the back of a Humvee, be 100 feet, 200 feet long, and flexible. You can put a bullet hole through it, and it will only lose the amperage equivalent to the area that it lost for the bullet hole size. Unaffected other than that. So there are some durability advantages to having amorphous or flexible solar panels. Longevity is normally not their strength, though. After 20 or 30 years, they've lost 20 to 30% or more of their possible production. A multi-junction cell is that layered cell that we talked about. They have more than one p-n junction. It is theoretical to have an N junction, and then a p type, and then an N type, and then a p type, and then an N type. And each place that they touch, if they are different materials, different elements, then they could absorb a different wavelength of the spectrum. That is why it is theoretically possible that in the future we may have solar panels that could actually have a layer in them that could collect X-ray, and at nighttime they would still be able to output a small amount of power. Maybe only. Yeah. Well, I mean, they're all passing through us right now, whether we enjoy them or not. So, the best laboratory efficiencies. I don't have a date on here, but I know that this is outdated. I'm just going to tell you right now. The most updated I have is the next sheet, but it is a little hard to read. Okay. For me, things practically impossible to read because of the colors. But it's very useful to get an idea of all the way back in 1975. Let's say whenever I was born. We're looking at 79. In 1979, the most efficient cells that we had were this one right here, and I believe that square is representing a single crystal, so a monocrystalline, non-concentrating cell. That panel's over there. Monocrystalline cell. We were looking at about 14% efficiency whenever I was born. Today, that same monocrystalline cell is at about 26% efficiency. Now, this is research cell efficiencies. This is not module efficiency. By the time that you get it into a real world module, you have losses and these efficiencies will come down. Make sense? We have, let's see here. These symbols always get to me. 4-junction, 47% efficient in about 2020, late 2019. Guys, I'm confident that sometime in 2021, we had new records. In 2022, we'll set more new records. All right, it's going to happen. Let's see if we can find the perovskite. They're considered an organic. Right here. So we've got this empty square. They began right here, and they have moved in 2016, 17, 18. Yeah, about 2019 is how new they are. They are already up to 24% efficiency. So they have reached with the newest thing, the newest technology. They have already reached a higher efficiency than we have reached with our monocrystalline cells. They're cheaper to make. They just won't quite last this long. Now, if we can get that stable, there's a good chance that 10 years from now, the market would be flooded with perovskite solar panel manufacturers.
That or possibly be so cheap that it doesn't matter.
Correct. Correct. Yeah. Labor
Always goes up.
always goes up. You picked up exactly what I was putting down. Labor always goes up. So this is what it looks like today. This is what it looked like when I began to teach. So I always leave this in my slide. I will forever. In 2011, this was the most recent slide that I could find, and we were only at sitting around 24% for our our standard monocrystalline panel, and perovskite wasn't even on here. Like they didn't even have it. Wasn't even a thing. Why didn't I think of that? Could have been rich. What time is it? All right, I think we're going to stop after this slide. So there are variables that determine the efficiency of cells. I need you guys to be able to calculate the efficiency based on the number of watts, the irradiance, and the watts per square meter in the area in meters. This is going to go in two different directions. I'll start with the simpler way. If I told you that this roof has 10 square meters of roof space that you could put solar panels on, I'm not going to be that nice to you guys. I'm going to give it to you in feet. You're going to have to convert it into meters. So if I were you, I would make sure that in your notes, you know how many square feet are in 1 square meter. Off the top of my head, I believe it's like 10.75 square feet in 1 square meter. But for simple math, if I told you that we had 10 square meters that we could fill with solar panels, and the solar panels that we are going to buy are 22% efficient, how many watts of solar panels could you fit onto that roof? Anybody? Well, how many watts per square meter is our solar constant? 1,000. So I'd take 10 square meters times 1,000 watts per square meter times whatever the cell efficiency is, 22%, so times 0.22. So 10 times 1,000 equals 10,000 times 22% efficient would be 2,200 watts of solar panels that you could put onto that roof. That's a really, really quick way of being able to tell how much solar panels can I get on this customer's roof. The slow way to do it is you look at the dimensions of your panels and you try to be like, well, I could fit this one up here in this way and this one up here in this way. Oh, well, we have all this extra space. Why? Because these panels don't fit easily into the dimensions that you have on the roof. You just want to start with a quick maximum. Sir or ma'am, you're only going to be able to fit about 2,200 watts of solar panels on your roof at the absolute most, but you need a 5,000 watt system. So would you rather have a large electric bill still and have a roof mounted system, or do you want us to design a more efficient energy wise but ground mounted system for you? The other thing that I may need to do for you is tell you that we have 24% efficient solar panels. There's 2,200 watts of them. How much space do they need? It's the same math, it's just reversed. So if I had 2,200 watts of panels, I'd take 2,200 watts. I would divide it by the efficiency. 2,200 divided by 0.22, which is 10,000. I divide by the solar constant of 1,000 watts per square meter, and I have 10 square meters. All right. Guys, if you struggle with this, it's you in your head. You're making it more complicated than you need to be. So take a step back and remember the two things: solar constant of 1,000 square feet, 1,000 watts per square meter. And remember, Andrew's not nice. He doesn't give it to you in meters, because I'm not. I'm going to give it all to you in roof dimensions in feet. Yeah, because that's the real world. It's the real world application for it. I know it sucks that the rest of the world uses metric and that we use the standard imperial system here. Go royalty, right? But we're not changing it. We don't have the influence to change the American system, and your customers don't know what meters mean. So don't talk to them about it. Talk to them about square footage. But do your conversions in your head. You can do it pretty simple. When in doubt, just go with 20%. 20% efficiency is pretty standard. Okay. Like, hey, I don't know what panels I'm going to use, so I can't do this calculation. Yes, you can. Use a standard 20% efficiency for rule of thumb. Monocrystalline panels will be a little higher than that. Polycrystalline panels will be almost right at that. And amorphous crystalline panels are going to be below that. But we can still get amorphous crystalline panels up to 16%, 17% efficiency now at the high end. Those can get a little more expensive, but yeah. When we get back, we're going to talk about the IV curves and really cover what all those mean. There's no point in starting it right now because we won't get through it. So that is it for the day, and we'll see you next time.